Welding Codes Overview, Welding Vocabulary for D1.1, Part 1. Okay, so this PowerPoint, just to give you a little background here. I've taken these PowerPoints off of the U.S. Nuclear Regulatory Commission. They had a Introduction to Welding Technology and Codes course. Well, over the last couple years, I've been hacking them up and putting stuff in and throwing extra stuff in. And anyways, I'm thinking I'm going to start trying to talk about AWS D1.1 in depth. And they covered a little bit of it, and I'm going to try and go in a little more in depth, throw in my insight, right, wrong, or otherwise, and we'll go from there. But that being said, the first parts are going to be, I'm going to put in some vocabulary. Because when you start talking about welding codes, you need to understand the language and have some vocabulary and understand a couple of the concepts. So a couple of these little PowerPoint presentations, or I guess they'll be YouTube videos at this point, we'll talk about some welding content and vocabulary and some subject material like that. And then we'll go off into D1.1. As you guys know, I'm like the king of chopping up other people's work. One of my superpowers, I guess, is being able to find non-copyright material in regards to welding on the internet. Nuclear Regulatory Commission, Can Teach, which is Can Do, the nuclear technology people from Canadian deuterium, uranium projects up there. They got a nice repository. Boilermaker One in Chief. It's an old welding manual for Boilermakers. The rate doesn't even exist in the U.S. Navy anymore. But a lot of really great material. I'm poaching the heck out of that stuff. Steelworker 3 and 2. It's a U.S. Navy course. I think I'm going to steal some stuff out of Machinery Repairman 3 and 2, and also Hull Technician 3 and 2. So any of you out there that want some good information on a budget, this stuff's pretty solid. It's good for most welding processes, and it'll give you the concepts. So a lot of the material that I'm using, it came from there. I poached it. I just might have added my own little bent on it, but that's where I got most of my stuff. I've kind of coalesced it into what you're going to see here. The American Welding Society. The American Welding Society publishes numerous documents covering welding and welding-related activities. AWS produces codes, specifications, recommended practices, classifications, methods, and guides related to welding. Their general subject areas are definitions and symbols, filler materials, qualifications, testing, welding processes, welding applications, and safety. The American Welding Society covers a lot of ground in North America in regards to welding. And as such, a lot of vendors and projects worldwide fall under American Welding Society standards, whether it's AWS D1.1 for structural steel or D1.14 for rebar. This is the organization. So when you see AWS, it means American Welding Society. This is a list of some of the publications that are put out by the American Welding Society. These are welding codes, or the first one's AB 2.1. It's the specification for welding procedure and performance qualification. I'll get into it later on a different YouTube rant. D1.1 is probably one of the most popular structural steel welding codes on the planet. D1.2 is structural welding aluminum. D1.3 is structural welding sheet steel. The difference between 1.1 and 1.3 is sheet steel is anything under 1/8 of an inch. Reinforcing steel, that's the rebar that goes in concrete, the reinforcing steel that goes in concrete. AWS D1.5 is bridge welding. Stainless steel structural is D1.6. D1.7 is structural welding, strengthening, and repair. D1.8 is the structural welding seismic supplement, and D1.9 is structural welding titanium. As you can see, AWS covers a lot of ground, and I'm going to try and take a shot at D1.1 first, and then we'll go from there. The overview of D1.1, the structural welding code, it's broken down into 9 clauses. I think they used to be sections and chapters, but now they're just called clauses. Basically a chapter. And I think to avoid confusion with ASME Section 9, Section 8, they just said these are clauses to avoid any confusion. So you can see the first one in D1.1 is general requirements. The second clause is design of welded connections. I don't generally dabble in that one. That's usually for structural engineers. I'm pretty strong and have dealt with a lot of pre-qualification of WPSs and qualification of WPSs. We'll hit those in the future. We'll also talk about fabrication, inspection, stud welding, tubular structures, and then strengthening and repair of existing structurals. You can see there's some annexes in there that are mandatory, and then informative and commentary and index. So the key with structural welding code, before we get into it, is just understanding how it's broken down. That there's different clauses that cover different areas that you might be dealing with. So it's kind of mental bookkeeping on when you're going into an argument or a discussion with somebody. You got to realize which clause of the code you're dealing with. Which subject area? Are we dealing with qualification? Are we dealing with pre-qualified WPSs? What are we talking about here? So hopefully, like I said, in the future podcasts, YouTube rants, I don't know what these are, we'll go through some of this subject matter. Properties of metals. So before we dive off into any of this, we should probably understand that there's some properties to metals, right? The physical properties of a metal determine its behavior under stress, heat, and exposure to chemically active substances. In practical application, the behavior of a metal under these conditions determines its mechanical properties, indentation, and rusting. The mechanical properties of a metal are important considerations in selecting material for a specific job. So this is telling us that each metal has a different property. That's why we don't build buildings out of copper. Copper doesn't have very good compressive strength, and it doesn't have a good tensile strength. It's good for utilization as an electric conductor or various other jobs. Maybe you need a big kettle to cook beer in, or fermentation. You probably want to use copper as opposed to something like steel. Titanium is a good material, but expensive. Aluminum is a good material for a lot of applications, but you couldn't construct buildings from aluminum because it might not have the toughness or the durability or the price point as steel and iron products. So as we go forward, you need to understand there's properties of metals. Each metal has different properties. Properties of metals. The particular properties that we require of any metal or alloy depends upon the use we will make of the material. For example, an anchor chain must have the property of toughness. A boiler tube must have high tensile strength, the ability to conduct heat, and the ability to resist deformation at high temperatures. An electric wire must be able to conduct electricity. A knife blade must have the property of hardness. A spring must be elastic. A saltwater piping system must resist corrosion. And a piece of metal that is to be drawn out into a wire must possess the property known as ductility. This section, we're going to talk about some of these important properties of metals and alloys, and hopefully increase our vocabulary a little bit and our understanding of some of these properties that are essential to understanding what we're going to be talking about a little bit in AWS D1.1. Types of loading. So when you're talking about welding codes, you need a lot of information from sciences and engineering categories and subject matters such as chemistry that aren't really welding, but they're kind of in that same general neighborhood, and they also intersect with welding. Well, one of the things that we need to talk about with welding is, and we're talking about welding codes, is types of loading. You can see this fine picture I poached from a U.S. Army manual, but it explains everything pretty good. You can see we've got tension, shear, compression, torsion, bending, and then I think there's malleability on there. You know, taking a metal and necking it down like you would a copper wire or a material like that. But we need to learn the language. So when somebody says a tensile test or talks about tension, oh, that's what tension is. This is shear. This is compression, torsion, bending. Because a lot of this vocabulary comes into play with AWS D1.1. And, you know, if some of you guys out there have been through all the engineering classes, maybe this doesn't apply to you. But maybe if you're a weld inspector or you want to brush up on your vocabulary, that's where I'm going with this podcast. So we're going to talk about vocabulary. I'm going to kind of talk about it like we're learning a language and maybe touch on this stuff. I'm not going to get too crazy into the math, just vocabulary. Types of loading, kind of a continuation of the previous slide. Tension, you can see in the upper right-hand corner, tension's one of the big ones that we need to understand because we talk about tensile tests or welded component that might be in tension. Compression is another important concept that we need to understand. You know, that's two forces pushing something together. Tension is something trying to pull it apart. Shear is when you have something like, it's like cutting something with a pair of scissors. That would be shear. Two forces acting parallel, but not, they're acting parallel, but they're not in the same line like they would be in tension. Torsion, that's twisting. Two forces moving in the opposite direction on the same body would be torsion. Bending, and then fatigue. Fatigue is a big one for some of the applications in AWS D1.1, at least I think, when you have, you know, the possibility of a cyclical member, you know, a member that is under different loads, different strains from different directions at different times, as opposed to just a static load, you know, a load that's just one place, one time. So once I couldn't throw this, just on a side note, I couldn't throw this slide away because I picked this one out of a U.S. Army manual also, and I like the pictures and how it shows, you know, the different types of loading. Tension stresses. Tension stresses are developed when a material is subject to a pulling action. If, for example, a cable is fastened to an overhead beam structure and a weight is attached to the free end, tension stresses are developed within the cable. The tension stresses resist the tension forces that tend to pull the cable apart. So here you can see we've got tension stresses. Two opposite forces pulling on an object. These are tension stresses. Tensile tests. Tensile tests are conducted using specimens cut from a test weld and machined to one of several standard sizes for mounting in a testing machine. Specimens are usually taken perpendicular to the weld, with the weld centered in the specimen as shown in figure 15-6. However, specimens are sometimes taken parallel to the direction of the weld and consist entirely of weld metal. Specimens may have round or rectangular cross sections depending on the requirements of the applicable welding code. The testing machine applies a tensile force on the specimen till it ruptures. From readings on the machine and measurements on the specimen before and after the test, properties such as yield strength, tensile strength, and ductility can be calculated. The primary purpose of the test is to demonstrate that the weld metal deposited by the selected procedure meets or exceeds the minimum values of specified in the applicable code. So basically, you're making a weld and then you're taking a slice out of that weld and you're machining it down, putting it in a tensile tester, pulling on it and making sure that the strength of the weld metal is equivalent or higher than the base metal. And this tells you what you need to know. You can get yield strength, tensile strength, and ductility out of this one set of tests. So tensile tests are a pretty good tool to have in your tool bag. Tension test, summary of method. Okay, for the tension test, we've got on the left, we've got the test coupon in the loading grips. So to figure out what the stress is in PSI, we'll use PSI because I think in PSI, the American/English system, you take your load, which is how much force it takes to make this specimen fail, and you divide it by the initial cross-sectional area. So 100,000 pounds divided by 1 square inch, it'll give you 100,000 PSI is your stress. Your elongation divided by initial gauge length is the strain. So you take your gauge length and then you figure out how much elongation there was and you divide it by the initial gauge length, and then that's your strain. Pretty easy math, pretty cut and dried. The tension test, summary of method. Tension testing of welded joints is done by a means of a calibrated testing machine and devices. The test sample is pulled in tension until the sample fails. The significance: tension test provides information on properties of welded joints, load-bearing capacities, joint design, and ductility. Here's a couple of tension test apparatuses. On the right, you can see a conventional loading system for tensile strength only. This is like the old school stuff from the 1950s. I don't know, 1950s, 1960s. This is what they had when I went to college. And then on the left, you can see a modern loading system that's computer controlled, and it'll give you a significantly larger amount of data than maybe the conventional loading system would. But you'll run across both, just depends on where you're at and what you're looking at. Both are quality ways to achieve the data that you're looking for or not looking for. Tensile test specimens. You can see that we've got an all weld metal tensile test here. You can see the red dot on the top illustration is where the tensile test was cut out of the weld. And an all weld metal tensile test is used to determine weld metal ultimate tensile strength, yield strength, elongation, and reduction in area. The reduced section tension test determines the ultimate tensile strength only. Specimens shall be tensile tested in the as welded condition unless the procedure qualification requires a post-weld heat treat. So what's this telling is that you can't do a weld test, do a test coupon, and send it to heat treat, and then pull the samples, and then and then the samples pass, and then you go out in the field and you're going to use that procedure without post-weld heat treat. If you have a procedure and you use post-weld heat treat, all the welds have to be post-weld heat treated. Compression stress. Compression stresses develop within a material to oppose the forces that tend to compress or crush the material. A column that supports an overhead weight is said to be in compression, and the internal stresses that develop within the column are compression stresses. You can see this figure shows compression forces and compression stresses. Basically, it's two forces pushing together, and it's trying to crush the material. That's what a compression stress is. So if you hear somebody talking about compression stresses, it's just two forces pushing together. It's not rocket surgery, but it's part of the vocabulary. So fancy way of saying pushing together is compressive stress. Compression stresses develop within a material to oppose the forces that tend to compress or crush the material. A column that supports an overhead weight is said to be in compression, and the internal stresses that develop within the column are compression stresses. Here you've got a couple of blocks and you've got some forces, and it looks like it's trying to crush an egg. That is compression stresses. Just two forces that are in alignment, pushing towards each other, trying to crush something. Compression stresses. Compression testing. Generally for steels, we don't do compression testing. We're big into tensile testing, impact testing, other kinds of testing. Compression testing is generally used for soils, concrete, and other materials normally loaded in compression. Samples are relatively low and wide, meaning they're kind of thick and fat but not very tall. Flaws are less critical in compression than they are in tension. The elastic limit, most metals about equal to tensile and compression. Cast iron has a tensile strength that is about half of the compressive strength. So this is what a test fixture would look like for compression testing. I used to work in concrete. We used to do a lot of compression testing because we needed to see how much of a load the concrete would take. So this is a general idea of a compression test. Shearing stresses are developed within a material when opposite external forces are applied along parallel lines in such a way as to tend to cut the material. Shearing forces tend to separate material by sliding part of the material in one direction and the rest of the material in the opposite direction. The action of a pair of scissors is an example of shear forces and shear stresses. The scissors apply shear forces, and the material being cut resists the shear forces by its internal shear stresses. So rivets are a big one where you would see something, or a bolt. If you had like bolts on a trailer hitch where something's being pulled apart, that would tend to shear that bolt off. I don't know if I'm giving a good example, but here you can see where we've got shear forces and shearing stresses. Torsional stresses are developed in a material when external forces are applied in such a way that they tend to produce rotation. A ship's shaft, for example, rotates when the external applied forces are greater than the internal torsional stresses developed in the shaft. Torsional stress is primarily a special form of shear stress, although it may also involve some compression stress and some tension stress. Here you can see this material being put into torsional stresses. It is being twisted. So twisting is a torsional stress on a part. A shaft, a drive shaft, or any kind of shaft, you have torsional stresses. Just a real quick thanks to everybody that's subscribed to my channel. I've looked through a lot of the names, and it seems to me that I have a lot of subscribers from South Asia, India, Pakistan, Sri Lanka maybe, some out of Bangladesh. I see some guys out of China and Korea on there. A lot of guys from the United States. I just want to say thanks. This kind of project, I just originally threw some stuff out there, didn't know if I'd get any hits or not. And now that I've gotten quite a few hits, I've decided to start putting out more content. So thanks everybody for subscribing, and you guys got my email address. If there's something in particular you think I might want to touch on, let me know. Questions? Here's my address, email address. If you want to hit my website, TexasWeldingEngineering.com, there's a handful of free things on there. I've taken military manuals and kind of gutted them and thrown a few things out there, but take a look. If you got questions or comments or maybe something that you want me to address in a little more detail, let me know and we'll see what we can do.